Hi everyone. For this video we're going to be looking at characteristics of what a function is, domain and range, and function notation. So let us begin. First we need to identify the difference between what a relation is and what a function is. Until this point you would have been studying relations in grade 9 and 10. A relation is a set of ordered pairs or coordinates with x and y values. It can be represented by a list of ordered pairs, a table of values, an equation, or a graph. Here are some of those examples right here. So we have an ordered pair in our first example, and essentially all we do here is we list a bunch of points that would belong in a table of values or on a graph. So for example, this point right here, we have x is equal to -2 and y would be equal to 4. You go on and you have 1, 2, 3, 4 more points listed in that relation. Something you're also familiar with would be a table of values. Again, we have our x, we have our y, and they're simply listed. Now these are the exact same relation as you see in the ordered pair, because if I were to list this as an ordered pair, I would have -2, 4, which was the first point in the first example. Next we have equations. This type of equation here, because the degree or the exponent, highest exponent is 1, is linear. If I rewrote the equation and changed some variables and constants, this here would be a quadratic. Also an equation and also considered a relation. And then we can also represent our relations as a graph like we did here, which is a parabola, which is essentially a quadratic relation. So up until this point we've looked at relations. Now we're going to dive deeper into what we call a function. In this course you will learn about functions. Functions are relations in which no two ordered pairs have the same x coordinate. In other words, every x value has only one y value. And we'll go through a number of examples just to identify to you what a function is so that we understand. So essentially you're looking at one of these examples, whether it's a list of ordered pairs, a table of values, an equation, or a graph, and you're wondering to yourself, is this an x value going to repeat itself? So first set of examples, we're looking at ordered pairs. Here are all my points in this first example: 3, 5, 12, -8, -4, 7, and 8 and 9. So in the first point, my x value is 3, okay? And my second point, my x value is 12. My third point, it's -4. And my fourth point is 8. Because none of those values are the same, there's no x value that is repeating, so every x value has only one y value associated. We would say, therefore, this is a function. Remembering that 3 dots in the triangle represents therefore. Okay, we look at the second example, and my x value for this first point is 5. My x value for the second point is -8. My x value for the third point is 5 again. Now we see this repetition. X equals 5 occurs twice because we have an x value of 5 that has a y value of 10 and an x value of 5 that has a y value of 4. That x of 5 has 2 y values and not only one, so we say therefore this is not a function. Pause the video now and see if you can do example C by yourself. Okay, third example, hopefully you got the same answer. It is a function because every x has only one y value. So that is how you identify whether or not you are looking at a function with a list of ordered pairs. Now let's look at a graph. Okay, when we look at graphs and we're asked is it a function or not, what you're going to want to do is what we call the vertical line test. Not too tricky. All you have to do is draw a vertical line over the graph. Once you do that, ask yourself, does a line cross the graph more than once? So let's do that. Okay. In this first one, we have a linear line on our graph. I'm going to draw a vertical line anywhere, it doesn't matter. Okay, and you see that it only crosses that graph right there. It does not cross anywhere else. If it only crosses once, you would say, therefore, this is a function. Same thing here. Now we have a parabola or quadratic. I'm going to draw a vertical line anywhere. Okay, we only see that it has one point of intersection or one point that it crosses. So you would say, therefore, this is also a function. And the last one, we're looking at a circle. Okay, so again, draw your vertical line. And what you notice here with the circle is I have 2 points where it crosses. Because that occurs, you would say this is not a function. If you ever asked to explain why it's a function or why it is not a function, you would say this is not a function because it fails the vertical line test. Take a second, review that, and then when you're ready, we will move on with the video. The next thing that we need to introduce is what we call domain and range. Okay, domain and range go hand in hand. Our domain is always associated with our x values, and our range is always associated with our y values. Okay, so the domain. The domain of a relation is a set of all x values that are part of the relation. So essentially, what can the graph equal in terms of x? In the table of values, what are those x values listed? And in the list of ordered pairs, what are all those x values? All of those x values listed would be the domain. On the other hand, you have the range. The range of a relation is a set of all y values that are part of that relation. So any value that relation, whether it's a graph, an equation, a table of values, or ordered pairs, any y value that it can equal must be present, and that would be the range. Below is a few examples of how we would write the domain and range. So this is new notation and symbols for everybody, so we'll go through this. Every part of your domain and range is going to be listed with this portion here, right at the start. Okay, so I could also, as you see, it's the letter D, so that one refers to domain. If I wanted to write range, then I would write it like such. But essentially, what that portion means, and I'm going to write it out, is so the range is an element of the real numbers. What that refers to, what a real number is just essentially a constant, can be a fraction or a decimal, basically any number that you're looking at, and it's one of the number sets. You could have irrational numbers, you could have natural numbers, but for this course we always use the real number system. So every time you are asked to list the domain and range, you're going to put either the domain equals x is an element of real numbers, or the range is an element of real numbers. And then you're going to put what we call the restrictions. So these are restrictions. The second part. Again, these would be restrictions here, and all the way at the end, these would be restrictions here. So if I want to write that, I'll continue my little example with range. Instead of x, I'm going to have y. So y is greater than 4. If if I read this whole thing out, it says range, and sorry, I need to correct this, it shouldn't have x, it should say y. The range is equal to y being an element of the real numbers, where y must be greater than 4. What that says to the person reading it is, if you're looking at a graph or table of values, every y value present there must be greater than 4. It can't be equal to 4, it can't be less than 4, it must be greater than 4. So whatever it is, for example, if I drew a little graph here, and let's say here is y equals 4, every value present in that graph is going to be greater or higher than that point. So those are your restrictions. That is your range. Okay, this portion here, sometimes you'll have to write the restrictions like this. What this is telling me is x is greater than 2 but less than 4. Okay, so it's more of a actual window of values as opposed to it has to be greater than one value or less than one value. So all the values of a graph or table value would be between 2 and 4s. And the last one, this one says x must be equal to 4. Meaning that the only point on that graph is 4. There's only one point, it's not a line, it's not a curve, it can't be greater than, it can't be less than, it only can be equal to 4 at that point. Domain and range takes a little bit of practice, so make sure you look at the examples and then do some of the suggested exercises to kind of help you get that practice. Okay, so let's move into a few examples here. So let's look at examples with domain and range. In this first example, we have a linear equation. Okay, we know that because the degree or exponent is only 1. With any linear equation, if you were to draw that on a graph, you would essentially have some sort of line that would extend forever and ever in both directions. What that basically means is that it's never going to stop. It's going to cross every x value and every y value. So there are no restrictions to this. When we're writing the domain and range for a linear equation, so let's do the domain. Domain where x is an element of real numbers, that's how you start all of them, that line, and there are no restrictions here. It can equal any value. So instead of that, just having that line, we're just going to have our closed bracket. Our range, same thing, it's going to extend forever, but we're not looking at x, we're looking at y. Y is an element of the real numbers. And that was domain and range for the first example. Every time you see a linear line or a linear equation, this will be your domain and range. Next, we have a list of ordered pairs. Okay, so the question is given us 3 points, 1, 2, and 3, and those are the only 3 points that exist in this relation. So, something I like to do is color code or signal the difference between your x and y values. So all my x values are there in yellow, and then my y values are highlighted in pink. So the x values are associated with my domain. So domain, again, you start it with x as an element of the real numbers. And now we're going to have restrictions. The restrictions here are 5, -8, and 5. So I have 2 values of 5 and 1 of -8. The only values it can equal are those. So I'm going to say x is equal to -8 or 5 and close bracket, because those are the only 2 values of x that it can equal. Now make sure when you do list values like this, if you get a question like this, that it's listed from smallest values to greatest values. That's why the -8 comes first. Take a second, see if you can come up with the range following the same pattern there. So for the range is equal to y is an element of the real numbers. Okay, And for this one, we see that our y values are 10, 7, and 4. Well, from least to greatest, that would be 4, 7, 10. What this says is the range is equal to y, an element of real numbers. Y can be equal to 4, 7, or 10. And those are the only values that exist. In this last example, we're given a bunch of points. Do not connect them, look at the points, and look at your scale. And my first thing would be to list those points. Write the coordinate right beside the point. Do that now. Take a pause on the video and try and write those out. I've done that. Hopefully we have the same points. With those points, you essentially have a list like you just did in example B. See if you can come up with the domain and range after listing those points out. Do that now. Take a few seconds. And here's what you should have got for domain and range. So domain, x is an element of real numbers. X can be equal to 0, 1, 2, and 5. Whereas the range is equal to where y is an element of the real numbers. Y is equal to 1, 2, 5, and 6. Okay, let's move on. Now we have some graphs. Okay, now of these three examples, there should be one that you can list without any assistance. If you look here, we have a linear equation, or a linear line, sorry. You know, with these arrows on both sides of it, that it extends in both directions. Therefore, every value is going to be possible. The domain, x is an element of real numbers, and there is no restrictions. The range, y is an element of real numbers, and there are no restrictions. But for our example in D, we actually have to do some restrictions here because we have a quadratic. These arrows right here tell us that it extends upward and that it's not going to go lower than this point right here, which, if we can recall anything from quadratics, is called the vertex. That point happens at 0, 0. So we're only looking at y values that are greater than 0. And although it might not look like it, because there's these arrows on the top of our parabola, it's going to get wider and wider and wider as the graph continues, and therefore it's going to cross every value of x possible. Therefore, for our domain for a quadratic, it's going to be x is an element of real numbers, and that will always be your domain for a quadratic. Whereas the range here, I just said that it has to be greater than that point 0. So y is an element of real numbers. Straight vertical line, we're going to list our restrictions. It's going to be a little bit different than the other examples, because now we want it to say y is greater than 0 or equal to, because it does actually touch that point. So y must be greater than or equal to 0, and that's your restriction. This symbol right here, if you want to make a note, greater than or equal to. See if you can do example F on your own here using the points on the circle that are kind of highlighted for you. So hopefully we got the same answers here, but let's review what I did. So for the domain is equal to x being an element of the real numbers, and this whole restriction section says that x must be greater than or equal to -1, that's that portion right there, but less than or equal to 7. And why did I say that? Well, this point right here, this is where, if you look up on the x-axis, x is equal to -1, and there is no values of x to the left of that, so it's not going to be any less than that. The other value right here, this is where x is equal to 7, and you notice that there's no values to the right of that. So all of your x values for this circle must be between -1 and 7, and that's why I've listed it like that. Same thing with our range. So the range, where y is an element of the real numbers, but y must be greater than -9, greater than or equal to -9, but less than or equal to -1. Well, here is -9, and you notice there's no values below it, so it has to be greater than that. And here we have the highest y value, the greatest y value, and that happens at y equals -1, so there's going to be no values greater than that, so it has to be between that range of -1 and 9, and that's why we've listed this. Y is greater than or equal to -9, but less than or equal to -1. Take some time to review domain and range, and then go back to the beginning of the handout to see the suggested exercises before we begin part 3. The last part of this video is going to go over what we call function notation. And notation is just a fancy way to consider how we're writing something in math. Up until this point, we've wrote things out in a certain way where you would see y equals an equation, whether it would be linear or quadratic. But we're going to change that up now. We're going to use a different type of notation, a different way to write that, because there's a few things that become a little bit trickier in this course moving forward. So suppose you were working with these two equations, and at some point in your work you ended up with the answer of y equals 4. The next day you look back at this work and you wonder how you got to y equals 4. So all you have is the answer, but not the process. What value of x did you use to get y equals 4? What did you sub in? The only way to tell this would be to look over all of your work. And as you know, sometimes in math, the process can be very long and tedious, and you don't want to go through the whole thing if you want a quick answer. So we have developed a new function notation that we could write these equations a little differently. So the old method, we have y equals 3x plus 1. In our newer method, I'm going to have this f bracket x equals 3x plus 1. And it's a little different. What that is, how I would say that is f at x or f of x. So I'm going to say, for this one right here, f of, oh, sorry, that's a little messy, f of x equals 3x plus 1. Same thing with the quadratic example. It used to be y equals x squared. Now it's going to be g at x, or g of x. Now I've used f and I've used g in these two examples. However, you can use any example. I could use h of x. I could use t of x. Sometimes it refers to the variables you're looking at in the question. So if I used h, maybe I was looking at height for some sort of variable. If I was using t, maybe I was looking at time for some sort of variable. It doesn't matter. The whole point of this is that I know when I have an answer what value I substituted into that equation to get that answer. So I don't have to look back over my work. I can just simply look at the final step. So when we sub into equation using function notation, we replace the x with the number as follows. So f of 1, this is what it says, f of 1. Now let's use the first example of the linear equation. So I have f of x is equal to 3x plus 1. I want to know what happens when I substitute 1 in for x. So I'm going to write it like this. F of 1 is equal to 3. I'm going to plug 1 in for x. Okay, and then I'm going to solve. Well, 3 times 1, that's 3, plus 1, that's 4. So now, if I had this final answer right here, f of 1 is equal to 4. What does that mean? Well, if I plug in x equals 1, I get y equals 4. So I know that this point, 1, 4, exists. And I know what I substituted in. If I do that with the second example, g of 2, well, I'm going to plug that in into my equation. I have x squared. Okay, if I plug in 2, 2 squared is 4, therefore g of 2 is 4. And I know again that I have the point 2, 4. Okay, it's just a little notation change. Does take some getting used to. All it takes is a little practice. So as I was saying, you can see that this notation allows you to see what x value was subbed in and which equation it was subbed into. So especially when you're working with multiple equations, this is helpful. So you see here we have one linear equation, one quadratic equation. If you had just simply an answer, you'd wonder, what did it belong to the quadratic or the linear? Now there's no need because I've separated. My linear equation is represented by f of x, my quadratic equation is represented by g of x. When we say f of 1 equals 4, this means that for the function f of x, the y value that belongs with x equals 1 is 4. And that's what I've highlighted here. And when we say g of 2 equals 4, this means that for the function g of x, the y value that belongs with x equals 2 is 4. And that was there. Okay, let's try and come up with a number of examples here that we can go through and get some practice. So, continue the video or pause and reflect on that a little bit if you need some extra time. So, for this last part here, we were given a number of examples and I've just rewrote the equations at the top there so we have them for reference. The first example, in A, is wondering what is f of 5 equal. So we're using this equation here because it's referring to f of x. So I'm going to write that out. F of x equals 3x plus 1. It wants to know if I substitute 5 in, so I'm going to write f of 5 equals 3, substitute 5 plus 1. Well, 3 times 5 is 15, plus 1 is 16. So f of 5 is equal to 16. If you wanted to list it as a point, it'd be 5, 16. Moving on to the next one. Now we're working with g of x. So what is g of 2? So first of all, write your equation that you're using. G of 2 is equal to x squared. I'm going to plug that in, substitute it in. And therefore, as we saw up top, g of 2 is equal to 4. If you want to list the point, it'd be 2, 4. Now things get a little trickier here. This question is here saying it wants us to solve what f of 5 is, take our answer, and subtract it from what g of 2 is. Now, we've already done that. In example A, we recognize that f of 5 is equal to 16. Okay. We recognize in our second that g of 2 is equal to 4. So what we need to do is simply write those numbers out. Well, f of 5 is 16, g of 2 is 4, 16 minus 4, that's 12. And that's your answer for C. There's no need to do that math all over again if you had done it in a previous question. But sometimes you might have to do those steps all together. Keep moving forward. We have f of 5 minus 2. Sometimes you'll notice in practice problems that they will do this. Really, just like you would do bed math, you have a little operation to solve inside the brackets. This becomes f of 3. So we're trying to solve what f of 3 is. We're going to use our f of x equation because it's referring to that one. We're going to plug in 3. 9 plus 1, that's 10. And f of 3 is equal to 10. Okay. Now, take a look at the last one, and I know there's a variable associated with it, but treat it the same way. Substitute that in and see what you get. See if you can remember how to do that. Pause the video and take a minute or two and see if you can figure that out yourself. So, perhaps you got the same question. So I started by writing out the equation. I substituted in 5x, not just 5 or not just x. Those things are associated together, so I substituted it in. And I multiplied, so 3 times 5x gives me 15x, and plus 1. And I can't combine these two things because they're not like terms, and that's my answer. So the answer to what is f of 5x? Well, it's 15x plus 1. So sometimes you won't get a full constant or whole number as your answer. Okay, now we're going to be looking at a graph example. Consider the following graph of the function f of x. So we have a parabola, a quadratic. It says determine the following. What is f of 0? What is f of negative 2? So essentially it's asking you for here, what is x when, what is y when x equals 0, and this one, what is y when x equals negative 2. Now you don't actually have to do any algebra here. We're just going to observe our graph and make a statement. So where is x equals 0? That would be right here. Okay, well, when that parabola crosses that point, what does y equal? You would say f of 0 equals 0, because y also equals 0 at that point. What about b? Where is x equals -2? It's right here. Okay, now I'm going to go up until I find where that crosses, and that's the point I'm looking for. If you look at that, that is where y is equal to 4. So f of -2 is equal to 4. In other words, when x is equal to -2, y equals 4. And lastly, to finish this off, an example when we look at an ordered pair. This one again we're just observing. So determine the following considering that this is a list of ordered pairs. F of 4. What is y when x is equal to 4? Well, just go through your points and see where you have that value. That's x equals 1, 2, 3. Here is x equals 4. The y value associated with that is 16. So therefore f of 4 is equal to 16. B. Where is f of 1? So you find where x is equal to 1. That is right here at the start. What is the y value associated? That's 1 as well. And lastly, what is f of 3 plus f of 2? Well, first of all, let's figure out what those two things are. F of 3 is equal to 9. Because there's x equals 3, y equals 9. F of 2 is here, and that is equal to 4. I simply want to add those two numbers, 9 plus 4, and you get 13, which would be your answer. That is the introduction to functions. We looked at domain and range, function notation, and characteristics of the differences between a function and relation. Review the video at certain parts, and enjoy.